to the third lesson in our series on electromagnetism. As you'll probably remember, in lesson 1 of this series, we investigated one of the links between electricity and magnetism. We showed that when a charge moves through a conductor, a magnetic field forms at 90 degrees to the direction of the moving charge. We can represent the magnetic field formed by drawing field lines in a circular pattern around the conductor. The direction of the magnetic field can be determined by using the right-hand rule. In this example, where the direction of the field is clockwise, the current moves into the page. This is indicated by a cross. It is important to recognize that the magnetic field continues around the whole length of the conducting wire and is not only found at one point. In this lesson, we will investigate how a current-carrying conductor can be used to make a useful magnet similar to a bar magnet. We call this sort of a magnet an electromagnet. We will start off by looking at the magnetic field formed around a single loop of wire, and we will then see how we can increase the strength of the magnetic field of this electromagnet. So, by the end of this lesson, you should be able to draw a diagram to show the magnetic field formed around a loop of wire, calculate the magnetic flux passing through a coil, explain how to increase the strength of a magnetic field formed around a loop, and plan an investigation to find out how different variables affect the strength of electromagnets. Your task for the previous lesson was to draw a diagram showing the field lines in a single loop. You could have worked this out by using the right-hand rule. Where the current is moving up, the curl of my fingers shows that the direction of the magnetic field is anti-clockwise. And here, where the current moves down into the surface, the curl of my fingers shows that the direction of the magnetic field is clockwise. These observations help us draw a diagram of the field lines around the conductor in the loop arrangement. For the diagram, imagine that the loop is cut in half and we are looking down on it. Compare your diagram to mine. Remember that the diagram represents a single conductor bent into a loop, even though there are two parts where the current moves in different directions. The current direction is indicated by a dot where the current moves up the loop and by a cross where the current moves down. The arrows on the field lines indicate the direction of the magnetic field. That wasn't too difficult, but remember that field lines cannot cross or overlap. So when a single conductor is bent into a loop, the magnetic field lines from the two parts of the conductor are squashed into the area inside the loop. Do you remember from the last lesson that a region where field lines are close together indicates the presence of a strong magnetic field? So here, inside the loop, the magnetic field is strong. You should also see that the direction of all the magnetic field lines inside the loop is the same, pointing out of the loop. Now look at the magnetic field on the outside of the loop. Here, the magnetic field direction is the same on both sides of the loop, but points in the opposite direction to the field inside the loop. Also notice that there are fewer field lines here than inside the loop. So here the magnetic field is weaker than it is inside the loop. So the effect of bending the wire into a loop clearly affects the shape of the field. Have you seen this pattern before? Of course, the shape is similar to the magnetic field of a bar magnet. Let's compare the magnetic field formed by a current-carrying conductor in a single loop to the magnetic field around a permanent magnet. Notice that in the bar magnet, the field lines inside the magnet run in the same direction close together and then loop around from the North Pole to the South Pole in two separate loops. Notice that the field lines are closest together at the poles and that they point out at the North Pole and in at the South Pole. The shape of the magnetic field of the bar magnet is very similar to the shape of the field formed by the single current carrying loop. In this loop, the magnetic field lines are also closer together inside the loop, indicating that there is a magnetic pole here. Can you figure out whether this side of the loop is a north or south pole? Well, since the field lines are pointing out of the loop here, this end of the loop must be the north pole of the electromagnet, and the other side of the loop must be the south pole of the electromagnet. Now that we have a clear picture of the magnetic field in a single loop, let's investigate how we can increase the strength of the magnetic field to make a more powerful electromagnet. What variables do you think we could change? Here are some I have thought of. Increase the number of loops of wire. Use different materials for the wire to wrap around. Increase the current in the wire. Let's start by increasing the number of loops of wire to make a coil. We call this a solenoid. One way to test the effect these variables have on the magnetic field strength is to use plotting compasses. I have placed them at regular intervals from the north pole of the coil. When the magnetic field is strong, the compass further away will be affected, but when the field is weaker, only the compasses close to the coil will be affected. For this experiment, I have a solenoid made from thick copper wound around a perspex core. We can connect the current to different numbers of turns on the solenoid. We are going to connect to 12 turns, 24 turns, and 36 turns. Let's test to see which of these arrangements produces the strongest magnetic field. Make sure you record your observations and come to your own conclusions for each of the experiments. For the coil with 12 loops, only the compass closest to the solenoid was affected. But for the coil with 36 loops, the compass furthest away from the coil was also affected. In other words, as the number of loops in the solenoid increased, so the compass needles further away were affected. We can conclude that the magnetic field increases as the number of loops increase. Next, let's see if the type of material used in the core of the solenoid changes the strength of the magnetic field. The solenoid we have been using has air in the core. When I used this solenoid with 24 turns in my previous experiment, the first two compass needles were affected, but the one furthest away was not. I will use this as my first reading. Next, I will insert a wooden rod to see if the magnetic field is affected. And now, I'll insert a soft iron rod into the core. How did the material in the core affect the magnetic field? Notice that only the solenoid with the iron core affected the compass needles further away. This means a solenoid with an iron core produces a stronger magnetic field than one with an air or wooden core. Why do you think this happens? When a rod of iron is brought near a magnet, the rod becomes a temporary magnet itself. This is exactly what happens when I place the rod inside the solenoid. The solenoid is an electromagnet and so magnetizes the iron. Now we have two magnets, the solenoid and the iron core. So overall, the strength of the electromagnet is increased. What do you think will happen when I increase the current passing through the coil? Well, in the last lesson, we showed that the magnetic field around a single metal conductor increased when the current increased. So we would expect the same result for a solenoid. Can you design an experiment to show that a larger current in a solenoid produces a stronger magnetic field? We suggest that you use the following simple apparatus, but you could choose any other apparatus available to you. Remember to think carefully about which variables need to be kept constant and which must change. You will also need to record your method, results, and your conclusion. What combination of variables do you think you would need to make a really strong solenoid? From all the experiments we have done, I think you can see that to make a really strong electromagnet, you would need a solenoid with a large number of coils, with a soft iron core, and a large current. Now I want to show you how to represent the magnetic field around a solenoid in relation to the current passing through it on a diagram. You will need to show the direction of the current, the direction of the magnetic field, and label the north and south pole. To begin, let's recall the diagram we drew for a single coil. In the diagram for the single loop, I had two circles representing where the current passed up and down. Now when I cut a solenoid in half and look down on it, I will see the ends of the conductor formed into two rows. On the diagram, I represent the cut ends of the conductor as circles. The circles in the row on the left all have the current flowing out and so have a dot in the center, while the circles in the row on the right all have a cross to represent the current moving in on this side of the coil. To help you complete the diagram for a solenoid with more than one loop, I want you to look carefully at what happens when you apply the right-hand rule to two conductors in the same row. Here the current is in the same direction, upwards, and you will see the magnetic field lines are in the same direction, anti-clockwise, around the conductors. Now if you look at two conductors in the other row where the current passes downwards, you will again see that the magnetic field lines are in the same direction, clockwise here. However, notice that in both rows between the conductors, the magnetic field lines oppose each other and cancel out. Can you now draw a completed diagram of a solenoid? Overall, the field line pattern is the same as for a single loop. The magnetic field lines point in the same direction inside the coil and in the opposite direction outside the coil. We can label the end of the solenoid where the field lines leave the coil as the north pole and the other end as the south pole. This completes our diagram of the magnetic field around the solenoid. Now I hope you can see that it is not difficult to determine the north pole of a solenoid by applying the right-hand rule. However, there is an alternative way which you may find useful. This is called the right-hand solenoid rule. Because there are many coils in a solenoid, the current direction is indicated by the curl of the four fingers, and the thumb points to the north pole. Let's apply the right-hand solenoid rule to this solenoid. Notice that the direction of the current is from the positive terminal and comes up on this side of the coil and down on the other in an anti-clockwise direction. If I curl my fingers over the coil, you can see that my thumb points to the left. The direction of the magnetic field inside the coil is shown as coming out of the coil by dots placed on the field lines. Now, if the direction of the current was changed to move in a clockwise direction around the coil, can you use the right-hand solenoid rule to show the direction of the magnetic field? Well, since the current is clockwise, here the direction of the magnetic field is into the coil here. We show this direction with crosses on the field lines. Now there is one more factor I want us to investigate. From these two diagrams, there does not seem to be much difference between the magnetic field of a solenoid with a single loop or one with many loops. However, if you take a cross-sectional view through the end of both solenoids, you can see that there are many more field lines passing through the cross-sectional area in the solenoid with many loops than there are when there is just a single loop. Remember, we used the term magnetic flux to describe the relationship between the magnetic field and the cross-sectional area through which the field line passes. In both loops, the area on the inside of the coil is the same, but there are more field lines passing out of this solenoid which has more coils in it. So the magnetic flux must be greater here. Electromagnets can be used to separate scrap metal. Only iron, nickel, and cobalt are magnetic metals, and these will be attracted to electromagnets, while other metals such as aluminium and tin will be left behind for collection and recycling. Electromagnets are also used in electric bells, relay switches, circuit breakers, electric locks, loudspeakers, and in electric motors. In fact, without electromagnetism, electricity would probably have remained a theory. Now, in today's task, I want you to examine these two coils. The one coil has a diameter of 5 centimeters, and the other has a diameter of 2.5 centimeters. The magnetic field of both the coils is measured as 0.1 Tesla. Calculate the magnetic flux of both the coils. Draw a field line diagram to show the difference in magnetic flux in each of the coils. Oosthuur's discovery that electric current could produce a magnetic field was only the first step in a long road in the development of electromagnetic theory. In our next lesson, we will examine the work of Michael Faraday, one of the greatest experimental scientists of the 19th century. He explored and found a way to use magnets to make an electric current. Do join me to find out about this very important discovery. Till then.